Imagine a future, maybe not too far off,
Right.
where we can really harness the unbelievable power of quantum computers to tackle problems that right now seem, well, completely beyond our reach.
Yeah, things like discovering new medicines or maybe designing materials with properties we haven't even conceived of yet.
Exactly, or even creating truly unbreakable codes for security. But that future isn't guaranteed, right? It really hinges on one crucial thing.
Making these quantum machines reliable and fast, like astonishingly fast.
Right, because the building blocks, the qubits,
Yeah.
they're the heart of it, but they're also the challenge.
That's the crux of it, absolutely. Qubits, the quantum version of classical bits, they're inherently unstable, super delicate,
Prone to errors, I gather.
incredibly prone to errors during operation.
Yeah.
So to make any progress, we absolutely have to be able to measure their state very, very accurately.
Okay, precision is key.
Precision, yes, but maybe even more importantly with breathtaking speed. And this whole challenge, it just gets harder and harder as the quantum processors get bigger.
As you add more qubits.
Exactly. Going from, say, tens of qubits to hundreds or maybe thousands in the future,
Yeah.
the difficulty just skyrockets.
So our mission in this deep dive is to really unpack a potentially groundbreaking solution to this fundamental problem. There's a team of researchers who have developed this really integrated approach. They're combining machine learning,
Specifically neural networks.
right, neural networks, with highly specialized hardware, these things called Field-Programmable Gate Arrays, or FPGAs,
Yeah, powerful little tips.
and their goal to basically perform this multi-qubit state discrimination, figuring out the state of multiple qubits in mere nanoseconds.
Which is just incredibly fast.
It's not just some technical feat, is it? It feels like a really critical step towards making fault-tolerant quantum computing, actually real.
It really is. It's foundational.
So we're going to dive deep into this. It's complex stuff, cutting edge, but we'll break it down, give you the key insights into how this innovation might unlock the full potential of quantum tech.
And why it actually matters to you right now.
Exactly. Let's get into it. Okay, so we always hear about the immense promise, right? Quantum computers solving certain problems way faster than any classical computer we have today.
Right. The potential is definitely there for breakthroughs in medicine, materials, cryptography, all those fields.
But you've already highlighted this big hurdle. These qubits, even with all that theoretical power, what makes them so fundamentally difficult to work with in practice?
Well, the power comes with this built-in fragility. Qubits are quantum systems, and that means they're inherently unstable, very sensitive.
Fragile how? What kind of errors are we talking about?
It's not just like a flipped bit in a classical computer. These errors can come from lots of places. For instance, you've got crosstalk.
Crosstalk.
Yeah, where the control signal or maybe the readout signal meant for one specific qubit accidentally affects its neighbors. It interferes.
Ah, like unintended interference.
Exactly. Then you can have spontaneous state transitions, a qubit just deciding to flip its state for no apparent reason due to environmental noise or internal processing.
It is randomly.
Well, seemingly randomly from our perspective.
Yep.
And then even the act of trying to measure the qubit,
The thing you need to do.
the essential thing, even that can distort it, cause unwanted excitations, push it out of the very state you were trying to measure.
Wow. Okay, I'm picturing trying to measure the exact spin of like a dozen really delicate spinning tops. And they're all wobbling if you even breathe on them, and maybe they're close enough that they're occasionally bumping into each other.
That's a fantastic analogy. It really captures the essence of the readout problem. Measuring a single qubit is hard enough because of these instabilities.
And doing it for many at once.
It intensifies exponentially as you scale up the processor. Imagine your wobbly tops, but now there are hundreds, maybe thousands, all interacting.
So how do they even attempt to read out many qubits simultaneously given the complexity?
Well, to manage the sheer resources needed, especially for readout, multi-qubit systems often use a technique called frequency division multiplexing.
Frequency division multiplexing, like
Right.
radio stations.
Kind of, yeah. It allows multiple qubits to be read out at the same time by assigning each one a distinct frequency.
Ah, okay. So you send in a signal with multiple frequencies mixed together, and each frequency interacts primarily with its assigned qubit.
Precisely. It's like broadcasting many signals at once, but you need to capture and analyze all of them simultaneously and accurately.
But even with different frequencies, that crosstalk you mentioned must still be a problem. The signals aren't perfectly isolated.
Exactly. Crosstalk remains a major, persistent challenge. Even with frequency multiplexing, the control and readout signals can still interfere,
leading to wrong results.
leading to corrupted measurements and potentially assigning the wrong state, saying a qubit is a 1 when it was really a 0, or vice versa.
So how do researchers actually measure how bad this crosstalk is? How do they know if their readout system is handling it well?
There's a key metric for that called cross-fidelity, or FCF.
Cross-fidelity.
Yeah, it basically quantifies the correlation between the measurement results of different qubits. It tells you how much measuring one qubit has affected the measurement outcome of another.
Okay, so ideally you want low correlation.
Ideally, you want almost zero correlation between different qubits. If you visualize this, like in figure 2 of the paper we're looking at, you'd see a matrix. High values off the main diagonal mean strong, unwanted correlations, lots of crosstalk.
You want a clean diagonal line, basically.
Exactly. A clean diagonal means you're successfully isolating each qubit's measurement.
Okay, so errors are just part of the deal with qubits, and measuring them accurately, especially with crosstalk, is tough.
This seems to lead directly to the need for error correction, right? Quantum error correction, or QEC.
Absolutely. QEC is non-negotiable if you want to build a truly fault-tolerant quantum computer. It's the strategy to deal with these pervasive errors.
How does it work in principle?
Well, the basic idea is to encode the information you care about redundantly. Use multiple physical qubits to represent a single logical error-protected qubit. Ah, like having backup copies.
Sort of, but it's more complex in the quantum world. Then, during the computation, you perform repeated measurements on some of these physical qubits, not to get the answer, but to detect if an error has occurred without disturbing the actual encoded information.
Okay, so you're checking for errors in real time.
In real time, yes. And if you detect an error, you apply a correction. Critically, this whole cycle, detect, diagnose, correct, has to happen during the computation before the errors pile up.
And I'm guessing this is where the speed comes in again. That cycle needs to be incredibly fast.
It's absolutely critical. The successful execution of QEC relies entirely on constantly monitoring groups of qubits and then swiftly invoking corrective actions.
Swiftly meaning nanoseconds.
Precisely. That swiftness means the post-processing of the readout signals the part where you figure out the qubit states from the measurement data must have extremely low latency.
So it's like that orchestra analogy again. If an instrument plays a wrong note,
you need to identify it and correct it before the next note is played. Otherwise, the entire symphony falls apart.
And the faster you can do that correction.
The more complex the music or computation you can play, the faster the QEC cycle, the more errors you can catch within the qubit's limited lifetime.
That lifetime being the coherence time.
Exactly. Qubits only maintain their quantum properties for a fleeting moment, their coherence time. If your readout and correction cycle takes longer than that, the QEC is useless. The information is already lost.
So low latency isn't just nice to have, it's fundamental. It dictates whether QEC can even work effectively.
It dictates the viability of fault-tolerant quantum computing. Speed directly enables robustness and allows us to tackle more complex quantum algorithms. It transforms QEC from a theoretical concept into a practical tool.
Okay, so the demands are immense. Precision, speed, dealing with crosstalk, all for effective error correction. It makes sense then that researchers are looking beyond traditional methods. And this is where machine learning, specifically neural networks, really comes into the spotlight for processing these qubit readout signals. What were people using before NNs became prominent?
Well, for a good while, the standard approaches involved techniques like matched filters. These are basically optimal linear filters for detecting known signals in noise.
Okay, a classic signal processing tool.
Exactly. And also support vector machines, or SVMs, which are a type of machine learning model good at classification tasks.
So machine learning isn't entirely new here, but NNs are different.
They are. While SVMs are ML, neural network-based discriminators have, in recent years, consistently shown a clear advantage in performance for this specific task.
Consistently better. How so?
Across different types of qubits, different experimental setups, NNs just seem to do a better job at post-processing these complex, noisy readout signals compared to the traditional methods.
What gives them that edge, especially thinking about reading out multiple qubits at once with that frequency multiplexing?
One really big advantage is how well NNs scale. Traditional methods, like matched filters, often require qubit-specific processing. You might need to digitally demodulate the signal for each individual qubit channel.
Which gets more complex as you add qubits.
Right. It scales, potentially, linearly or worse, with the number of qubits. Neural networks, however, can often process the entire multiplex signal holistically. They can look at the combined signal and learn the intricate patterns within it.
Ah, so they don't necessarily need that separate processing step for each qubit?
Often, no. And maybe even more importantly, NNs have proven to be exceptionally good at mitigating that readout crosstalk we keep talking about,
How do they manage that?
because they can learn complex nonlinear relationships in the data. Crosstalk often manifests in subtle nonlinear ways that simple filters miss. NNs, with their layered structure, can effectively learn to disentangle the signals, figuring out the state of one qubit even when it's being subtly influenced by its neighbors.
They learn to filter out the noise and interference automatically.
Exactly. They learn the specific fingerprint of crosstalk in a given system and compensate for it.
Okay, that sounds incredibly powerful for tackling these key challenges. But there's always a but, isn't there? Neural networks, especially the powerful ones, are known to be, well, computationally hungry.
That's the catch. You've hit on a critical bottleneck. Despite all these advantages, getting these NNs to run on the kind of hardware you need for real-time quantum control like those FPGAs has been a massive challenge.
Why? What's the specific issue?
It really boils down to the sheer storage and computational demands. A typical NN, even one that's not astronomically large by modern AI standards, can have millions of parameters.
Parameters meaning the weights and biases, the things the network learns.
Precisely. These parameters define the network's learned function, and there could be millions of them.
Can you give us a sense of scale? How much memory would a typical network for, say, 5 qubits take up?
Sure. Let's look at a baseline model mentioned in the research called Arch-1. It takes in 1,000 input values, has 3 hidden layers with 1,500 and 250 nodes, and 32 output nodes.
Okay, sounds reasonably complex.
That network alone has over 1.6 million learnable parameters. Now, if you store each parameter using standard precision, like 32-bit floating point numbers,
Which takes 4 bytes per number.
right, the weights and biases alone would need around 50 megabytes of memory.
50 megabytes, that doesn't sound like much for my laptop, but for an FPGA.
For an FPGA, that's often huge. FPGAs are optimized for speed and parallelism using fast on-chip memory, like block RAMs or ultra RAMs. These are incredibly fast, but also relatively limited in capacity compared to the DRAM in your computer. 50 MB can easily exceed the available on-chip resources.
So the powerful brain doesn't fit in the fast body, essentially.
That's a good way to put it. You have this conflict. You need the NN's intelligence, but it's too resource-heavy for the hardware that can deliver the required nanosecond latency.
Which leads us to the core innovation here. How do you bridge that gap? How do you make these NNs fit without crippling their performance?
The key lies in a technique called quantization.
Quantization sounds like making things discrete.
Exactly. It's a process to drastically reduce the model's storage and computational needs by representing everything, the parameters, the activations, the inputs, using low-precision numbers instead of those high-precision floating point values.
So instead of 32 bits per number, you use fewer, like 8 bits or 4 bits.
Or even just 2 bits, or 1 bit in some cases. Think of it like compressing a high-resolution digital image. You reduce the number of bits used to represent each pixel's color.
But doesn't that lose information? Doesn't the image quality, or in this case, the network's accuracy, suffer?
It can, if done naively, but the trick is to do it intelligently. You can often reduce the precision significantly with only a minimal impact on the final accuracy.
How? How do you do it smartly?
A particularly effective method is quantization-aware training, or QAT.
Quantization-aware training. So you make the network aware it's going to be quantized while it's learning.
Precisely. You simulate the effects of low-precision arithmetic during the training process itself. The network learns to be robust to the noise and limitations introduced by quantization right from the start.
Ah, so it adapts its parameters to work well even with fewer bits.
Exactly. It allows the parameters to be pushed down to very low precision, sometimes even binary, just ones and weens, while often maintaining high accuracy.
And this is what the researchers used.
Yes, they used tools like Bravitas, integrated with PyTorch, which are specifically designed for this. These tools allow for really flexible quantization. You can choose different bit widths for different parts of the network, like maybe 4 bits for inputs, but only 2 bits for weights.
Mixed precision.
Mixed precision, exactly. Finding the optimal balance for each part of the network.
Okay, so QAT is the magic ingredient that lets you shrink the NNs enough to fit onto the FPGAs without losing too much accuracy.
It's a crucial enabler. It makes these advanced AI models practical for resource-constrained real-time hardware.
And the implications go beyond just this specific readout problem.
Oh, definitely. Being able to run complex, quantized NNs efficiently on hardware like FPGAs opens up a lot of possibilities. For QEC, it means faster processing, which allows for more error correction cycles within that critical coherence time. That directly boosts the overall robustness of the quantum computation.
More corrections mean fewer final errors?
Right. And beyond QEC, it could enable other sophisticated techniques. Imagine integrating reinforcement learning agents directly into the control system, learning optimal control pulses in real time.
Wow, adaptive quantum control.
QAT and efficient hardware implementation are foundational steps towards those kinds of advanced autonomous quantum systems. It's about making AI a practical, integrated part of the quantum stack.
Okay, we've got the fragile qubits, the need for speed via QEC, and how quantized NNs offer a path to accurate, fast readout. Now let's really focus on the hardware platform itself. Why FPGAs, and specifically these RFSC devices you mentioned? What makes them the right choice here?
FPGAs, field-programmable gate arrays, are really key because they offer this unique combination of high-speed parallel processing and, crucially, reconfigurability.
Reconfigurable hardware,
Right.
meaning you can change what the chip does.
Exactly. Unlike a standard processor, like a CPU or GPU, which has a fixed architecture, an FPGA's internal logic can be reprogrammed after manufacturing to implement custom digital circuits.
Why is that so important for quantum computing?
Because quantum computing is still a rapidly evolving field. The control sequences, the readout protocols are constantly being refined. FPGAs let researchers quickly implement and test new ideas directly in hardware, achieving the low latencies needed without having to design a whole new custom chip every time.
So flexibility meets speed. And what about the RFSoC part? What does that add?
RFSoC stands for Radio Frequency System on Chip. These are a special type of FPGA that integrates high-performance analog-to-digital converters, ADCs, digital-to-analog converters, DACs, directly onto the same chip as the programmable logic.
Ah, the converters that bridge the analog quantum world and the digital processing world?
Precisely. Having them integrated directly on the chip is a huge advantage. It minimizes the distance signals have to travel, reducing noise, and critically minimizing latency. For qubit readout, where you're dealing with faint, high-frequency analog signals, this tight integration is transformative.
So the RFSoC is like an FPGA supercharged for handling these specific kinds of quantum signals.
That's a good way to think about it. And implementing these NN-based state discriminators directly on the RFSoC fabric offers a significant leap over traditional signal processing. You get higher throughput, much lower latency, essential for that real-time QEC feedback loop.
It really is the digital brain talking directly to the quantum processor. What specific RFSoC did this research team use?
They use a Xilinx RFSoC ZCU111 evaluation kit. The chip on that board, the XCU28DR, is pretty powerful. It has 8 high-precision RF DACs and 8 RF ADCs built right in.
8 of each. And you mentioned they're fast.
Very fast. The DACs can run up to about 6.5 gigasamples per second, and the ADCs up to about 4 gigasamples per second. And they're low power too, which is important.
Those speeds sound astronomical. Why do you need such incredibly fast converters for talking to qubits?
Well, the qubit signals themselves and the control pulses needed are often in the microwave frequency range, gigahertz. To accurately generate those precise microwave pulses with the DACs, and to capture the subtle, fast-changing qubit response signals with the ADCs without losing information or introducing distortion, you need these very high sampling rates.
Oversampling, essentially, to catch all the detail.
Exactly. And these converters are tightly coupled to the FPGA's programmable logic using standard interfaces like AXI stream, which are like high-speed data pipelines within the chip.
So the converters are the crucial interface, translating between analog quantum signals and the digital bits the FPGA and the neural network can work with?
They are the critical link. They turn the faint whispers from the quantum processor into digital data the NN can understand, and turn the NN's decisions back into precise analog control signals.
Okay, let's picture the lab setup. It sounds like quite an intricate dance. Can you walk us through it? Where does it start?
Sure. If you look at Figure 1 in the paper, it lays it out. At the heart of it, you have the quantum processor itself, in this case, 5 superconducting transmon qubits.
Superconducting, so they need to be cold.
Extremely cold. They're housed inside a dilution refrigerator, which keeps them at about 20 millikelvin. That's just a tiny fraction of a degree above absolute zero. necessary to maintain their quantum properties.
Okay, qubits in the deep freeze. What about the RFSoC?
The RFSoC board, with all its processing power, sits outside the fridge at room temperature
How do they connect?
through carefully shielded coaxial cables that run into the refrigerator. The RFSoC generates the precise microwave pulses needed to control the qubits and to read them out.
Let's follow a readout pulse. Where does it go?
Okay, a readout pulse starts as a digital pattern in the FPGA logic. It goes to one of the RFACs, gets converted into a precise analog microwave signal,
At gigahertz frequencies.
potentially, or at an intermediate frequency that then gets mixed up to the qubit frequency. This analog pulse travels down the COPA cable into the fridge, interacts with the qubit, or its readout resonator.
And picks up information about the qubit's state.
Exactly. It acquires a state-specific characteristic, maybe a subtle phase shift or amplitude change, depending on whether the qubit is a 0 or a 1.
Okay, the signal now carries the quantum information. What happens next?
That modified signal travels back out of the fridge, likely gets amplified by very low noise amplifiers along the way, and then hits one of the high-speed RF ADCs back on the RFSC board.
Back into the digital world.
Right. The ADC digitizes the returning analog signal.
And how does that frequency multiplexing fit in when reading all 5 qubits?
Instead of sending 5 separate pulses, they generate a single combined pulse. This pulse, maybe lasting a microsecond, is actually made up of 5 different frequencies, superimposed one for each qubit's readout resonator, but likely at lower intermediate frequencies, IFs first.
So frequencies like 64 megahertz, 25 megahertz, etc., all mixed together.
Exactly. That combined IF signal then gets up-converted using a microwave local oscillator, say, at 7.1 gigahertz to the actual readout frequencies needed inside the fridge.
Okay, clever. One pulse talks to all 5.
Then, after that pulse interacts with all 5 qubits and carries back their combined state information, encoded in the phase amplitude shifts at each specific frequency, the same local oscillator is used to down-convert the returning signal,
Bringing it back down from gigahertz.
bringing it back down to a range the ADC can handle efficiently, maybe sampled at 500 megahertz in this case. This down-converted signal still contains all 5 frequency components, each carrying the information for one qubit.
And that digitized multiplex signal is what finally gets fed to the neural network on the FPGA.
Precisely. The ADC outputs the signal as its fundamental components, the in-phase I and quadrature Q parts. These IQ data streams, containing the information for all 5 qubits, are then fed directly into the FPGA logic where the quantized neural network accelerator is implemented.
And the NN spits out the state of each qubit.
It processes the IQ data and infers the state 0 or 1 for each of the 5 qubits.
And then comes the feedback loop for QEC.
If needed, yes. Based on the states inferred by the NN, the FPGA logic can immediately generate a feedback signal. This signal might trigger corrective pulses sent back through the DAGs to the qubits. It closes the loop. Measure, infer, correct, all happening within nanoseconds, orchestrated by the RFSoC. That speed is everything for making QEC work.
All right, the hardware setup is clear, this intricate dance between the cold qubits and the room temp RFSoC, mediated by those super fast converters. And we know quantized NNs are the key to interpreting the signals quickly. But getting those NNs, even quantized ones, to be both accurate and fit efficiently onto the FPGA, that sounds like where the real engineering artistry comes in.
It really is a balancing act. You can't just take a standard NN architecture, quantize it, and hope for the best. You need to optimize the architecture itself, with the hardware limitations and the quantization in mind.
So how did they approach that? Did they start big and trim down?
They did. They started with that baseline model we discussed, Arch-1. Remember, 1,000 inputs, 3 hidden layers, 500, 250 nodes, 32 outputs, quite large.
And likely too slow and resource hungry, even quantized.
Exactly. So they began strategically streamlining it. First, some standard practices, like adjusting layer sizes to be powers of 2, which often mapped better to hardware memory structures.
Makes sense for efficiency. What else?
A more significant change was reducing the input feature size. Instead of 1,000 raw IQ samples, they use a technique called boxcar averaging, or integration over segments of the signal to compress the 1 microsecond measurement down to 512 input features.
So pre-processing the input slightly to make it smaller without losing too much information, hopefully.
Right. But the really crucial optimization, the one that had a massive impact on scalability and efficiency, was changing the output layer.
Going from 32 outputs down to 5.
Exactly. Instead of having the network try to classify which of the 25 equals 32 possible combinations of qubit states occurred.
Which gets exponentially harder as you add qubits.
Right. Instead, they redesigned it so the network makes an independent prediction for each qubit. Is QIB 1 a 0, 1? Is QIB 2 a 0, 1? And so on. There's 5 outputs.
How do you train a network to do that?
You use a specific type of loss function during training. In this case, something called binary cross-entropy with logits loss. BCE with logits loss. It's designed for multi-label problems where each output is an independent probability.
Ah, so it's not picking one winning state out of 32, but giving a probability for each qubit being 0 or 1 independently.
Precisely. This change makes the network exponentially more scalable. Adding another qubit just means adding one more output node, not doubling the output layer size. It's a much more efficient way to represent the problem for the hardware.
That's a huge architectural insight. What impact did these changes, reducing inputs, shrinking hidden layers, and especially changing the output structure, have on the actual performance? Did the accuracy hold up?
That's what Figure 3a in the paper explores beautifully. They systematically tested different configurations. Reducing the input size from 1024 down to 512 had almost no effect on the geometric mean fidelity, FGM, the metric they use for overall accuracy, maybe a 0.3% drop at most.
Wow, negligible. What about the hidden layers?
Similarly, reducing from 3 hidden layers down to just 1 and drastically cutting the number of nodes in that layer also had only a marginal impact on fidelity until they went too far.
There's a tipping point.
Exactly. They found that configuration with 512 inputs, a single hidden layer of 64 nodes, and the 5 outputs, 512 by 64 by 5, offered a really good balance. It was much smaller and faster, but the FGM was still high. Shrinking it further than that caused the accuracy to drop off rapidly.
So they found the sweet spot for the architecture itself. Lean, but still powerful enough.
Yes. It strongly suggested you could significantly reduce the model size without sacrificing much readout fidelity.
Okay, architecture optimized. Then came the fine-tuning of the quantization, right? Finding the right number of bits.
Right. Having settled on a more compact architecture, they then meticulously explored the impact of different bit widths for the inputs, the weights, and the activations within the network. They tested everything from 8 bits down to 2 bits.
What did they find there? Was everything equally sensitive to bit reduction?
Not quite. The results, shown in Figure 3b, c, and d, were quite clear. The input quantization was the most sensitive.
The raw data coming in?
Yes. When they quantized the input signal to below 4 bits, the fidelity started to degrade noticeably. At 2-bit input quantization, the FGM dropped significantly, down to around 0.7.
So the input signal needs at least a certain level of precision, like 4 bits, to capture the necessary details for accurate discrimination, at least for this 5-qubit system.
That seems to be the case. You need enough granularity in the input data.
What about the weights and activations, the internal parts of the network?
They found more flexibility there. Using mixed precision, like maybe 2 bits for weights and 4 or 8 bits for activations, didn't seem to hurt the fidelity much. The network was quite robust to low precision internally.
But going too low still caused problems.
Yes. When they tried using binary quantization just 1 bit for both weights and activations, there was a definite drop in accuracy. Fidelity fell by somewhere between 4% and 21%, depending on the exact configuration.
So binary networks, while super efficient in terms of hardware, might be too much of an accuracy trade-off for this particular task.
It seems so. That final bit of precision seems important here.
So based on all this testing, what quantization scheme did they finally settle on?
They landed on using 4 bits for the input signal and just 2 bits for both the weights and the activations.
4-bit input, 2-bit weights, 2-bit activations. Why that specific combo?
It represented the best trade-off. The 4-bit input preserved the crucial signal information, while the 2-bit weights and activations dramatically reduced the memory footprint and computational cost, allowing it to fit efficiently onto the FPGA, but without the significant accuracy loss seen with fully binary networks. It hit the sweet spot of high fidelity and hardware efficiency.
Makes sense. Now, the ultimate test, did this optimized quantized network actually do a better job of handling the crosstalk problem compared to traditional methods?
Yes, and this is a really important result. Figure 3F shows the cross-fidelity matrix for their optimized QNN compared to a traditional matched filter.
And the QNN looks cleaner. Significantly cleaner. The off-diagonal elements, which represent the crosstalk interference between qubits, are much smaller for the QNN. It clearly shows the neural network is far superior at isolating the individual qubit signals and mitigating the effects of crosstalk.
So it learned to ignore or compensate for the interference between qubits much better than the standard filter?
Exactly. It demonstrates the power of the NN to handle those complex, nonlinear interactions that plague multi-qubit systems.
Okay, so let's recap this section. By carefully optimizing the network architecture, especially that clever output layer change, and then applying strategic mixed precision quantization based on detailed experiments, they created a neural network model that is, 1, small enough for the FPGA, 2, maintains high measurement fidelity, and 3, is significantly better at fitting crosstalk.
That sums it up perfectly. It's a multi-pronged optimization approach that tackles the core challenges head-on, paving the way for robust, hardware-accelerated readout. We've got the optimized quantized neural network recipe. Now, how do you actually bake that into the FPGA hardware to achieve those target nanosecond latencies? You mentioned QEC needs ultra-low latency for mid-circuit measurements. This sounds like we need specialized tools for the hardware implementation itself.
Absolutely. Just having a quantized model isn't enough. You need a way to translate that model into highly efficient parallel hardware logic on the FPGA. And for achieving the lowest possible latencies, data flow architectures are often the way to go.
Data flow architectures, what's the core idea there?
Instead of a traditional processor fetching instructions and data, a data flow architecture creates a dedicated hardware pipeline specifically for the computation. Data flows, or streams, directly between processing elements custom-built for each step of the calculation, like layers in a neural network.
Minimizing data movement and control overhead.
Exactly. It maximizes parallelism and minimizes latency by having data constantly moving through the pipeline. And a key tool the researchers use to build this kind of architecture is a framework called FINNR.
FNNR. What makes it suitable for this task compared to other ways of getting NNNs onto FPGAs?
Well, traditional approaches have drawbacks. You could try to design the hardware by hand, writing low-level hardware description code, but that's incredibly time-consuming and requires deep hardware expertise.
Not practical for rapid iteration.
Not at all. Or you could use generic high-level synthesis HLS tools, which let you write C++ code and try to automatically generate hardware. That's faster, but often less flexible, and might not produce the absolute lowest latency or most efficient result, especially for specialized things like quantized NNs.
Okay, so FINR offers a better balance.
FINR aims for the best of both worlds. It's an automated framework specifically designed for mapping quantized neural networks onto FPGAs, using these efficient data flow architectures. It offers more automation than hand coding, but more flexibility and potential for lower latency than generic HLS or some overlay-based frameworks.
Why lower latency specifically? What's its advantage there?
A key reason is its focus on using on-chip memory and that streaming data flow approach. It avoids going off-chip to slower external memory whenever possible. Everything flows through dedicated pipelines on the FPGA fabric itself, which is crucial for hitting those nanosecond targets needed for quantum systems.
Okay, so how does FINR actually work? What does it take as input, and what does it output?
It typically starts with a description of the quantized neural network, often in a standard format like ON and X, Open Neural Network Exchange. This description needs to include metadata specifying the quantization details, the bit widths for weights, activations, etc., which can be exported from tools like Provitus within PyTorch.
So it needs the network structure and the quantization info.
Yes. FINR then takes this description and automatically transforms it into a streaming data flow graph. Each node of the graph, representing a layer or operation in the NN, gets mapped to a hardware module, often described using HLSC++ that Xilinx tools can understand.
And it has special blocks for the quantized math.
Right. It uses specialized hardware building blocks called multi-vector threshold units, or MVTUs, which are highly optimized for performing the low-precision matrix multiplications and thresholding operations that are common in quantized NNs. One MVU might handle one layer, for instance.
And you mentioned a trade-off between resources and speed.
Yes, FINR allows for flexibility there. For a given layer, you can choose how much hardware parallelism to dedicate. You could use fewer hardware units and process the data in chunks over time multiplexing, to save resources. Or you could dedicate more parallel hardware units to process everything faster at the cost of using more FPGA area.
Tailoring it to your specific needs. But even with FINR and data flow, you hinted that FPGAs have limits, like connection bandwidth. How did that become a problem, and how did they overcome it for maximum speed?
That's a really critical point. Even with data flow, if one layer needs to send a huge amount of data to the next layer all at once, the connections between those hardware blocks on the FPGA can become a bottleneck. The AXI stream interface, which acts like the data highway, has a limited width or number of lanes.
So if a layer has many inputs and outputs, it might overwhelm the connection.
Exactly. For moderate-sized NNs, especially in the first layer, which might connect to many input features, this connection width can limit the achievable parallelism and thus increase latency. You can't run everything as fast as you want if you can't get the data there quickly enough.
So the researchers had to get creative with the hardware architecture itself, even within the FINR framework.
Yes, they designed some novel hardware architectures specifically to address this AXI stream bottleneck and push the parallelism even further.
Tell me about one of these novel architectures. This sounds like deep hardware design.
Okay, let's look at the novel segmented architecture, which they called Arch7. This was based on that optimized 512 by 64 by 5 network. The really clever idea was how they handled that hidden layout with 64 nodes.
Instead of one block of 64.
They divided into 8 smaller equal segments. Each segment implemented just 8 nodes of that hidden layer, including the necessary math, batch normalization, activation function.
Okay, 8 mini layers running side by side. How did the input connect?
Crucially, the full 512 input features were connected to all 8 of these segments simultaneously. So each segment sees the full input, but only calculates its assigned portion of the 64 hidden node outputs.
Ah. And because each segment is smaller.
Each segment is much smaller and requires significantly fewer input connections than trying to connect all 512 inputs to all 64 nodes in one monolithic block. The total connection requirement for that layer dropped dramatically from potentially needing over 32,000 parallel connections to just about 4,000 per segment.
Making it feasible to run all 8 segments fully in parallel on the FPGA.
Exactly. This segmentation completely eliminated the need for time multiplexing within that critical first hidden layer. Everything happens in parallel, which dramatically reduces the latency contributed by that layer.
That's a really smart way to overcome the interconnect limit by breaking the problem down physically on the chip. Did FINR handle this automatically?
Not quite out of the box. They had to make some modifications to ensure the segmented model could be correctly processed by the standard FINR flow. This involved inserting some specific quantidentity layers before combining the outputs of the segments and adding some custom steps to the FINR transformation process.
So they adapted the framework to support their novel architecture.
Yes, it shows the power of combining automated tools with clever domain-specific hardware design. This segmented approach allowed them to achieve ultra-low latency, even with a network that might traditionally be considered too large for full parallelism due to interconnect limits.
Very impressive. Was there another alternative approach they explored for low latency, maybe one better suited for deeper networks?
Yes, they also looked at a piecewise layered QNN architecture, seen in Arch 8 and Arch 9. This was an alternative strategy, particularly useful if you needed a deeper network for more complex feature extraction.
How did that work? Deeper usually means slower, right?
Not necessarily with this design. The core idea is to structure the network so that different layers process different segments of the input signal sequentially, but in a pipeline fashion.
Like a relay race for the data.
Kind of. Imagine the input signal divided into chunks. The first layer processes the first chunk. The second layer processes the second chunk plus the output from the first layer. The third layer processes the third chunk plus the output from the second layer, and so on.
Okay, so later layers depend on earlier ones, but how does that help latency?
The clever part is that the critical path latency, the time that determines the overall readout speed, is primarily determined only by the processing time of the last layer, because the earlier layers can be working in parallel on earlier parts of the signal stream. The last segment of the input signal only gets fed into that final layer.
Ah, so even if the network is deep, only the time taken by that final stage really counts towards the final results delay.
Exactly. It allows you to implement deeper networks, perhaps with smaller individual layers, while still keeping the overall spate discrimination latency extremely low. It's another ingenious way to structure the computation for speed on the FPGA.
Okay, we've seen the quantum challenges, the optimized NN software, and these incredibly clever hardware architectures designed within FINR to exploit FPGA parallelism and beat latency bottlenecks. Now, for the bottom line, what were the actual results? Did all this work pay off in terms of speed, accuracy, and efficiency?
The results, laid out quite clearly in Table I of the paper, are really impressive. Let's start with that big baseline model, Arch 1, the one with 1.6 million parameters. They actually managed to implement it on the FPGA using the 4-bit input, 2-bit wait, 2-bit activation quantization.
The full big one.
Yes, And the accuracy, the geometric mean fidelity, FGM, was 0.904. That's only 0.9% lower than the accuracy reported for the same network using full floating point precision in earlier work.
Wow. So the quantization really did preserve the accuracy remarkably well, even for a large network.
It absolutely did. But, as we suspected, Arch 1 was still relatively slow in hardware terms. Its latency was over 3,800 nanoseconds. Good proof of concept, but not fast enough for QAC.
Right. So how did the optimized architectures fare, that 512 by 64 by 5 network, Arch 5?
That's where things get exciting. Arch 5, being much smaller and architecturally simpler, brought the latency way down to 127 nanoseconds. And the fidelity was still excellent at 89.91% FGM, a huge improvement in speed with minimal accuracy cost.
Okay, 127 nanoseconds is getting much better. But you mentioned those novel architectures pushed it even further.
They really did. Let's look at Arch 7, the segmented architecture designed to maximize parallelism. It took the latency down from 33 clock cycles for Arch 5 to just 19 clock cycles.
Almost half the cycles. What's that nanoseconds?
That translates to an incredible 47.12 nanoseconds. So under 50 nanoseconds for discriminating the state of 5 qubits simultaneously.
That's blisteringly fast. Did it use a lot more FPGA resources to achieve that parallelism?
It did use more resources, yes. About 25% of the FPGA's lookup tables, LUTs, compared to maybe 10–15% for the simpler Arch 5. That's the trade-off. More parallelism needs more hardware logic. But it was still well within the chip's capacity and achieved that crucial speed boost.
Under 50 n's. And what about the other novel approach, the piecewise layered network, Arch 9?
That one was even faster in terms of latency. Arch 9 achieved a latency of just 24.03 nanoseconds, only 9 clock cycles.
Wow. Just 24 nanoseconds. That's truly phenomenal speed.
Yeah.
And the accuracy.
Still very good. FGM was 89.07%. This really shows the power of that piecewise architecture for achieving ultra-low latency, even potentially with deeper networks if needed.
So they demonstrated multiple paths to get well below that critical 50 nanosecond threshold, depending on whether you prioritize absolute minimum latency or perhaps a slightly simpler architecture.
Exactly. They showcased a toolkit of techniques delivering state-of-the-art speed.
And you mentioned the resource usage. Even the faster, more parallel Arch 7 only used about 25% of the LUTs. Does that leave enough room on the FPGA for everything else needed in a quantum control system?
It certainly suggests so. Remember, the original huge Arch 1 only used 39% of the LUTs. These optimized architectures, Arch 4 to Arch 9, show a range, but even those resource-intensive ones leave significant FPGA fabric available for other essential tasks: pulse-generation logic, sequencers, communication interfaces, maybe even parts of the QEC decoding logic itself.
So the N accelerator doesn't consume the whole chip. It's a component within a larger system.
Precisely. And they even showed an extremely resource-light version, Arch 6, using binary weights and activations. It used less than 5% of LUTs. The fidelity was lower, but it shows the spectrum of possibilities depending on the exact requirements.
Okay, this performance sounds amazing. How does it stack up against other recent work trying to do similar things using NNs for qubit readout? Is this truly state-of-the-art?
It really appears to be at the forefront. Table 2 in the paper provides a comparison. Some previous work, like Royer et al., reported excellent latency, around 48 ANs, but that was for a single qubit system with a much smaller network, fewer than 2,000 parameters.
So comparable speed, but simpler problem. What about multi-qubit comparisons?
Another relevant work by Moria et al. Did implement a deep NN for frequency multiplexed readout, similar to this work. However, their approach still needed qubit-specific demodulation steps before the NN, which potentially limits scalability, and critically, they didn't report the end-to-end latency, which is the key figure of merit here.
So it's hard to compare speed directly. How do the latencies from this work compare then?
The latencies achieved here are 49.6 Ns for Arch 7, including interface overheads, and 26.7 Ns for Arch 9 are right there with, or arguably better than, the best reported latencies, especially considering this is for a multi-qubit system without pre-demodulation.
And what about the complexity or robustness of the networks themselves?
That's another crucial advantage. The networks implemented here, like Arch 7 and Arch 9, have significantly more parameters, around 33,000 and 42,000 respectively. That's 18 to 29 times more parameters than the single qubit network from Royer et al.
Why is having more parameters an advantage here? Doesn't that usually mean slower?
More parameters, in this context, suggest the network has greater capacity to learn complex patterns and potentially generalize better to different noise conditions or slight variations in the system. It makes the solution potentially more robust and versatile for handling the complexities of real multi-qubit readout, including crosstalk. And the fact they achieve these low latencies despite the larger network size highlights the effectiveness of their optimization and hardware acceleration techniques.
So it's fast and potentially more capable and scalable.
Exactly. The methodology is shown to be scalable. They could even implement the 1.6 million parameter network, and it delivers leading performance without needing those qubit-specific preprocessing steps, making it inherently well-suited for systems with increasing numbers of qubits.
That's a compelling package. Now, just briefly, you mentioned they also looked at support vector machines, SVMs, as an alternative. What was the takeaway there?
Yes, they included an appendix on SVMs. SVMs are another type of machine learning classifier, generally simpler than deep NNs, but often very effective, especially for cleaner decision boundaries than, say, simple thresholding.
And how did they perform on the FPGA?
They implemented a quantized SVM using 8-bit precision for the 5-qubit system. The result was remarkable in terms of speed and efficiency. The discriminator latency was just 5.74 nanoseconds.
5 nanoseconds? That's astonishingly fast.
It is, and it used minimal resources, only about 1675 LUTs. It represents an incredibly efficient, ultra-lightweight hardware solution.
So when might you use an SVM instead of a neural network?
An SVM might be a great choice if the problem is simpler, perhaps single-qubit readout, or situations with very low crosstalk where you need the absolute bare minimum latency and resource usage. It showcases that for some scenarios, a simpler ML model, when properly implemented in hardware, can offer incredible performance. It adds another tool to the quantum engineer's toolkit. #outro.
So we've taken quite a journey here, deep into the core challenges of building reliable quantum computers. We've seen how fragile qubits and the need for error correction demand incredible speed.
Nanosecond speed.
And we've unpacked how this research provides a powerful solution, using scalable neural networks, carefully optimized through quantization.
That crucial step of making them fit.
Right, shrinking them smartly, and then deploying them onto these specialized FPGA platforms, using clever hardware architectures like segmentation or piecewise processing to achieve truly ultra-low latency.
Getting that multi-qubit state discrimination down below 50 nanoseconds, even below 25 nanoseconds in some cases.
Which, as you've emphasized, isn't just about bragging rights for speed. That dramatic reduction in the time it takes to process the readout signals is what directly enables quantum error correction to work effectively.
Exactly. It allows for more QEC cycles within the qubit's coherence time. More cycles mean more chances to catch and fix errors before they wreck the computation. It makes the whole process much more robust.
Ultimately improving the performance and really the viability of building larger, more useful quantum processors. This feels like a really critical step towards making practical quantum computing a reality.
It genuinely does.
Yeah.
And it's a robust, scalable approach, too. It doesn't rely on those complex, qubit-specific signal processing steps, which means it's well-positioned to handle systems as we scale up to more and more qubits.
It's also fascinating to step back and see how advancements in seemingly classical technologies, sophisticated machine learning algorithms, advanced quantization techniques, reconfigurable hardware like FPGAs are becoming absolutely essential tools for pushing the quantum frontier forward.
It's a real synergy. Classical computing innovation is directly enabling quantum progress.
Which leads to a final thought, something for you, our listeners, to mull over. As we keep pushing these boundaries, the tools we use AI, specialized hardware, are becoming almost as complex and fascinating as the quantum systems they help control. So what other breakthroughs might be waiting at the intersection of seemingly different fields? What other classical innovations, maybe from areas we haven't even considered yet, could unlock the next big leap in quantum technology? What other fundamental bottlenecks do you think could be broken by creatively integrating these advanced, yet perhaps currently separate technologies?